Hello, welcome to another module in this massive open online course. So, we are discussing about the LMMSE estimator, that is the linear minimum mean squared error estimator, that is given a quantity y bar, how to estimate, how to find the best linear estimate of another correlated vector x bar, right, such that the mean squared error is minimized, alright. So, that is the LMMSE principle, which as I have already told you has several applications in the context of estimation. So, we are talking about the LMMSE estimator, and what we have showed so far is that I have norm of expected value of norm of x bar minus x hat whole square, where x hat, remember this is a linear estimator, this is of the form C y bar. This can be expressed as, well, this can be expressed as trace of r x x minus trace of r x x minus c r y x minus r x y c transpose plus c r y y c transpose, and to this what we are doing is we are adding and subtracting this quantity plus r x y r y y inverse r y x minus r x y r y y inverse r y x. So, we are adding and subtracting this quantity essentially, okay, and that is minimize the trace of this whole quantity. So, adding and subtracting. So, adding and subtracting this quantity, and therefore, now if we want to minimize this, that becomes equivalent to minimizing this quantity that we have just written over here, alright. And this you can see essentially, if you examine this deeply, what we are trying to do is essentially we are trying to complete the square over here, as you are going to see, and we can write this, you can check this, this can be written in a very nice compact form as minimize trace C r y y minus r x y into r y y inverse C r y y minus r x y, right, transpose plus r x x minus r x y r y y inverse r y x, okay. So, this can be simplified in this fashion, and now you can see that this quantity here, if you look at this quantity, this is a constant in the sense that does not depend on C. Remember, we are trying to find the best C that minimizes the mean square error, right, constant, that is does not, this does not depend on C implies I can write this as minimize trace of CRYY minus RXY times RYY inverse CRYY minus RXY transpose plus RXX minus RXY times RYY inverse RYX, which is a constant. So, this comes out of the minimization, and you are left with this first term essentially, right, because the second term is essentially a constant that does not depend on the matrix C. Okay. And now if you look at this, to minimize this quantity, now note that this quantity, if you look at this RYY inverse, this is interesting because RYY, remember RYY is a covariance matrix, right. This is basically, if you remember, this is basically expector y bar transpose. So, this essentially implies that, remember, any covariance matrix is positive semi definite. This implies that RYY, right. So, this implies that RYY is a positive semi definite matrix. This implies that this quantity, that is trace of C RYY minus RXY into RYY inverse C RYY minus RXY, this quantity is always greater than or equal to 0 because RYY is PSD. Implies minimum of this occurs for above occurs when the quantity equal to 0. When the quantity is equal to 0, right. That is obvious because it is always greater than or equal to 0. So, the minimum value of this is naturally this is equal to 0. And therefore, now for this to be minimum, that occurs, when does the minimum occur? Remember, it is a positive semi definite matrix. Minimum occurs only when CRYY equals, implies CRYY equals RXY, which essentially implies that C equals RXY times RYY inverse, implies C equals RXY into RYY inverse, right. And therefore, this implies now that X hat equal to C y bar, which implies X hat the best, that is the linear minimum mean square error estimate of X bar is RXY RYY inverse into Y bar. This is the LMMSE estimate. So, it is very simple, it is a very simple structure. This is the LMMSE, that is again linear linear minimum mean squared error estimate of x bar. All right. So, that is the LMMSE estimate of x bar. And what is the minimum error corresponding to this? The minimum error corresponding to this, right. If you look at this, remember the first term is reduced to 0. If you take a look at this, the first term, this term can be reduced to 0, right. This term reduces to 0, implies error equal to the second term. All right. So, therefore, the minimum error, if you very easy to deduce, the minimum MSE becomes trace of RXX minus RXY, RXX minus RXY times RYY inverse RYX. This is the minimum MSE, and in fact, if you look at this, this is nothing but the error covariance matrix. Matrix for the LMMSE. That is, if you ask the question, what is expected value of x bar minus x hat into x bar minus x hat transpose, that is going to be given as RXX, right. That is essentially what the error covariance is, that is your RXX minus RXY times RYY inverse into RYX. Okay. So, this is your LMMSE error covariance matrix. This is the LMMSE error covariance, and so that is essentially, that answers both the questions, what is the LMMSE estimator of x bar, right, in terms of the correlated vector y bar, and what is the covariance, error covariance of the LMMSE estimate. And now, let us look at the other case, that is, generalize this when x bar comma y bar are not when x bar y bar are not 0 mean. This implies that you have expected value of x bar is equal to 0, expected value of y, I am sorry, expected value of x bar equal to mu bar x, which is not necessarily 0. This is mu bar y, not necessarily 0. Okay. Now, what we do is very simple, you subtract the mean, form the 0 mean quantities x bar minus mu x bar, we form y tilde equals y bar minus mu bar y. Now, note that these are 0 mean quantities. Now, you have subtracted the mean. So, you have got these are 0 mean quantities. Essentially, we have expected value of x tilde equal to 0 and expected value of y tilde equal to 0. So, we can use our LMMSE estimator that we have just derived for the 0 mean quantities, and therefore, I can write the estimate of x tilde hat. This is going to be r x tilde y tilde times r y tilde inverse times y bar, which is nothing but, remember now writing this as x hat minus mu bar x equal to r x tilde y tilde, sorry, this will also be y tilde, r y tilde inverse times y bar minus mu bar y. This implies that x hat equals r x tilde y tilde r y tilde inverse times y bar minus mu bar y. Now, let us ask the question, what are these quantities r x tilde, r y tilde and r x tilde y tilde. There is the covariance matrix of y tilde and the cross covariance between x tilde and y tilde. And it is very easy to see that these quantities are nothing but r y tilde equals expected value of y tilde transpose, which is nothing but expected value of y bar minus mu bar y into y bar minus mu bar y transpose, which is nothing but r y y, covariance matrix of y bar. Similarly, r x tilde y tilde, this is equal to the expected value of x tilde minus, or expected value of x bar, this is expected value of x tilde y tilde transpose which is nothing but expected value of x bar minus mu bar x into y bar minus mu bar y transpose, which is equal to, right, r, which is equal to r x y. So, you have r x tilde y tilde equal to r x y, and therefore, finally, we can write, this implies that we have a very simple expression for the LMMSE estimate x hat equals r x y r y y inverse y bar minus mu bar y, correct. I am sorry, here you have to have mu bar x that comes from the right, left, mu bar x. So, therefore, you have plus, you have, this is essentially the expression that one obtains for the LMMSE estimate. Once again, this is the LMMSE estimate of once again, this is basically your LMMSE. This is basically your LMMSE estimate in terms of the this thing. Okay. So, that essentially completes our derivation of the LMMSE estimate, both for, of course, first for the 0 mean quantities x bar and y bar, and where the quantities are general, that is the mean is not equal to 0, and you can in fact observe something very interesting. So, what happens here is if x bar and y bar are uncorrelated. Now, let us look at an interesting case. If x bar and y bar are uncorrelated, now this implies that r x y equal to 0. If you look at this, if r x y equal to 0, x hat is simply equal to mu bar x. So, this implies, very interestingly, if you look at this, this implies x hat equals mu bar x, that is it. So, very interestingly, x hat reduces to mu bar x, that is the best estimate of x is simply the mean. Because y bar does not convey any additional information about x bar, because the cross correlation r x y equals 0, right. So, this also implies that y bar, observing y bar does not convey any additional y bar does not convey any additional information about x bar. So, therefore, the best is having observed y bar, your knowledge about x bar or your estimate of x bar does not change, and the estimate of x bar is simply the mean, that is mu x bar, which you had said anyway if there was no observation to begin with. So, if you have a random vector and there are no observations, and if someone asks you what is the best estimate that you can, or the best prediction that you can make of a random quantity without any observation, is essentially that the best estimate would be the mean of that random quantity. Now, because x bar and having observed y bar, if x bar and y bar are correlated, you would expect to make a better guess or a better estimate of x bar, but unfortunately, if x bar and y bar are uncorrelated, observation y bar does not help, and the best estimate of x bar is still the mean, which also goes to show that the better the correlation, the stronger the correlation between x bar and y bar, the better is your estimate of x bar going to be, and that is in fact if you look at this expression, that is in fact reflected in the error covariance. If you examine this again, you will notice that this error covariance is r x x minus r x y r y y inverse r, implies greater r x y greater the cross correlation. Of course, these are matrices, so you cannot say one is greater, one is lesser, but intuitively greater r x y implies lower error, right. So, what you can see is that if r x y, if the correlation is strong, the resulting error will be lower because your prediction of x bar is much better, all right. So, these are essentially some very interesting things that fall out from analyzing this LMMSE estimator and LMMSE estimation principle in general, all right. So, let us stop this discussion here and we will continue in the subsequent modules. Thank you very much.